Okay, so now that we've discussed the forces on a fluid volume, the next step is to apply the linear momentum theorem to a pure fluid control volume. So essentially we're going to move these terms to the right-hand side of this integral, and then we're going to make some assumptions and derive a differential form for what we call inviscid fluid. Okay, so now we're going to write the equation for the general equation. This is actually the general linear momentum theorem for a fluid, that's partial by partial t integral rho u dv over the control volume plus the momentum fluxes rho u dot n ds is equal to the integral over the control surface of minus p n ds plus the integral over the control surface of t dot n, so this is t dot n ds or tds, so tau dot n ds plus the gravitational body force for the control volume rho g dv. Okay, so you notice here there's a change in notation. We'll get to that later. Okay, so now in the interest of getting to a differential form, which is what we're after in this course, we're not just looking for integrated quantities. We want to get pointwise information about the velocity field and the pressure, so we need governing equations for these pointwise velocities and pressures. So this is going to be our next step. We're going to assume now that there is there are no stresses, no viscous forces. Assume no viscous forces. So there's motion, there's going to be motion in the fluid, but we're going to neglect this guy. We're going to say that this guy is 0. Okay? And then we're going to manipulate this equation to get into a differential form. So we're going to assume a fixed control volume to get everything into a control volume form integral. So we get partial by partial t of rho u, control volume. We can move the time derivative inside, plus. Now, this is going to be an interesting term. If you remember the divergence theorem, it applies for scalars, also applies to vectors. And we're going to spend some time discussing the meaning of the divergence here, but bear with me for a second. If you remember, the divergence theorem said that the integral of phi n ds, okay, over a control surface. So that's the gradients theorem. It's just going to tell us that this is over the control volume of grad phi dv, but also that the integral of some vector u dot n ds, that's equal to the integral of the divergence over the control volume. Okay, so this is the control surface. Now the same thing applies here, okay, where in this case we have a vector quantity for phi. Okay, so we have a vector quantity for phi, and that's actually, so this whole thing would be a tensor. So then our integral is going to be integral over the control volume of div rho u dv. Okay, so think of this form. This is a quantity dotted by a unit normal over here. In this case, this is the quantity that we're dotting with the unit normal. That gives us this divergence form. So this is a tensor dyadic. This is a tensor. This is the effective tensor. And the divergence of this tensor is going to give us a vector. Okay? We'll talk about this in a second. Now on the right hand side, we're going to use this gradient theorem to convert this guy into a volume form. So we have a minus integral over grad P dV. Really, this is the pressure force over the volume. It's just the pressure gradient that matters over the control volume. Plus, this is already in volume form, integral of rho G dV. Now we're going to make the same argument that we did before and say since the control volume is arbitrary, the above is true if the integrands are equal. So integrands, if you move everything to the left hand side, for example, integrand equal to 0, so that d rho u by dt plus div rho u is equal minus grad p plus rho g. And that is the general Inviscid flow equation, or Euler's equation. So this is Euler's equations. These are Euler's equations, or Inviscid flow equations for both a compressible and incompressible fluid. For both compressible and incompressible fluids. Now, let's just spend some time thinking about this equation. It just tells you that the acceleration of a fluid element is balanced by pressure gradient and the body force that is exerted on the fluid. Okay, or the body, these forces cause the acceleration and are balanced by each one of those. Now, I want to pay some attention to this term, and there are two ways that I like to think about this. One of them is really easy, and I highly recommend. The other one can get a little bit nasty, but let's spell out these equations. Again, they're vector equations, so in Cartesian coordinates, write them again. Over here we have partial rho u by partial t plus div rho u equal minus grad p plus rho g. In Cartesian coordinates, so in Cartesian coordinates, it's x, y, z. Okay. All of the other terms are easy to just spell out, except for this guy can get a little bit complicated. One easy way to think about this is start by writing the individual components. So we have d rho u by dt, and then d rho v by dt, and then d rho w by dt. These are the three components. Plus, now think about something here. If you can think of this guy to be related to that guy, okay, this is if you choose the x component here, you're going to have to choose the x component there. And so that this term would be div rho u vector u, okay, so that makes it the divergence of a vector, and equal to minus dp by dx, that's the x component, plus rho gx. Same thing here for the rho v component, so choose rho v and choose rho v over here. These are the same quantities, so that gives you div rho v u equal minus dp by dy plus rho gy. And finally, same thing, d rho w, so rho w, choose rho w here, choose rho w there. This gives you d rho w u equal minus dp by dz plus rho gz. Now, these guys, very easy. Div rho u vector u. Now remember the vector u is uvw, right? So that gives you d rho u by dx plus d rho u v by dy plus d rho u w by dz. Same thing here. This guy gives you div rho v u is equal partial rho v u by partial x plus partial rho v v by partial y plus partial rho v w by partial z. Same thing here. Div rho w vector u is d rho w u by dx plus d rho w v by dy plus d rho w w by dz. Now, there's another way that you can do this. Remember the dyadics and the divergence. The second way of looking at this div rho u, second approach to div rho u, is look at the tensor dyadic. So first remember that the dyadic vector, the way we wrote that was, so a, b, we wrote this as a1, a2, a3 times b1, b2, b3. So our rho u vector we're going to write as rho u, rho v, rho w times u, v, w. And so first column, first row, that gives you rho u, first column, second row, that gives you rho u, v. So you start seeing these components. First column, first column, third row, that gives you rho u, w, same thing here, rho v. So that's the second row, first column, second row, first column, that gives you rho v u, and then rho v v, and then rho v w, and finally rho w u, rho w v, and rho w w. And then when you take the divergence of this quantity, you're going to take the divergence of this vector, and that vector. So think of these as the individual vector components of rho uu. So this is ex, ey, ez. So then you do the div rho u. You're going to take the divergence of this guy, and that's going to be the component in the x direction, and this one is going to be the component in the y direction, and the divergence of this one is going to be the component in the z direction. So that gives you d rho u by dx plus d rho u v by dy plus d rho u w by dz. That's ex, and then so you get this nice column vector, okay? So that's d rho u v u, etc., ey, and then ez. One last note on this Inviscid, on these Inviscid equations is that these equations are actually coupled with the mass conservation law. And so this particular form is called the strong or conservation form of the equations. But there's another form that many people prefer to use. So let's write the governing equations, actually. So the governing equations for inviscid flow. And I forgot to put that on the previous lecture. So they're actually d rho by dt plus div rho u equals 0. That's continuity, mass conservation. And d rho u by dt plus div rho u equal minus grad p plus rho g. Okay. Now, this form is what's called the conservation or strong form of the equation. It just says that you're transporting the conserved quantity, and what's conserved here is momentum. Okay, so that's momentum per unit volume, that's rho u, that's what's being conserved here. But there's another form that we can turn this equation to. So if you take this guy and split the time derivative and this term, so we're going to start by splitting the time derivative. We know that d rho u by dt is equal rho du by dt plus u partial rho by partial t. And for the other term, div rho u, is a vector identity, and this one is going to be u div rho u plus rho u dot grad u. Okay, well, pay attention to this. This is u div rho u. It is, so this is scalar. U div rho u is a vector. Rho u dot grad u is also a vector because this is a tensor dotted with the vectors is going to give you a vector. Okay, so when we do these substitutions, we're going to add these together. You get rho du by dt plus u d rho by dt plus u div rho u plus rho u dot grad u is equal to minus grad p plus rho g. Now what do you notice? That if we collect these two terms together, factor out u, this is partial rho by partial t plus div rho u, that's equal to 0 because this is continuity. So that we get what we call the weak form of the equations. It's du by dt. I'm going to divide by the density also. So du by dt plus u dot grad u is equal minus 1 over rho grad p plus g. That's pretty neat. Okay. Now, and coupled with the mass conservation equation, you still need to satisfy mass conservation. So you better satisfy mass conservation, otherwise this guy will not be valid. But as long as mass conservation is satisfied, this guy will be valid. Okay? But you cannot just use it alone. Just because you made the assumption that it's 0, it doesn't mean it's going to satisfy mass conservation. Okay? So you have to use this equation in conjunction with the mass conservation equation. It's completely valid, continuously, mathematically. Now, from a numerical perspective, we have to deal with some other issues, but because you have errors in satisfying continuity, and then you may not be solving the full set of equations. These guys, you may be solving something else if you just solve this guy. But that's a discussion for another course. Right now, you can legitimately and completely use this equation. This is still valid for a varying density and compressible flow. It's just the form is a little bit different. Many would rather use the strong form because it transports the conserved quantities. Okay, and when you're transporting the conserved quantities, you know, in compressible flow theory, moving across a shock, the integration of these equations may be easier. You don't have to worry about dealing with density or pressure kind of discontinuities. Okay. So we will be using either one of those equations depending on the problem. They're completely legitimate. Some people call this the weak form of the Euler equations. Finally, note the components of this vector over here are equal to u du dx plus v du dy plus w du dz x plus u dv dx plus v dv dy plus w dv dz ey plus the third component u dw dx plus v dw dy plus w dw dz ez.